Assalamualaikum and hi students. So this is a lecture video for BEKG 2443 Engineering Mathematics 2. We are still in chapter 2 multiple integrals, and in this video we will cover the 6th and 7th LOs where we evaluate triple integrals in Cartesian coordinates in over non-rectangular region and triple integrals in cylindrical coordinates. 2.6 triple integrals over non-rectangular regions. So there are three possible types of a region not in the shape of rectangular box. So the first type is when we integrating over simple xy solid. For type 2 over xz solid, and the last type 3, we integrating over simple yz solid. For type 1 region, a solid region G that lies between the graph of two continuous functions of x and y, bounded upper and below by this domain G. Okay, so you know the domain for x, y and z. Okay, where R is the projection of G onto the xy plane as shown in figure below. So basically for type 1 region, we have R, the base is on xy plane. And the triple integral can be expressed as follows. Okay, we have triple integral, and we solve for dz first and then followed with dA. dA is the base. Either you do it dx, dy or dy, dx. So this is for the first type. For this example, okay, if G is the region in the first octant enclosed by the cylinder y square plus z square equal to 1 and the plane y equal to x, evaluate triple integral G for function z dv. So basically, we need to start with sketching the region. So first, we have z and y plane because we have y square plus z square equal to 1. So you know this is a circle with radius 1. So you have a circle with radius 1. And then you have another region in yx plane where you have y equal to x. So y and x. Y equal to x is here, somewhere around here. And then y is equal to 1. Y square plus z square equal to 1. So you know intercept at y here is 1. So you have this region R here. So this is 1. When we combining these two sketching, these two planes, these three planes, we have 3D. In 3D, we have z, y, and x. And then for z and y, we have a circle in the first octant. Okay, so we have a quarter circle with radius 1. And then we have for y and x, we have this line. So basically, this is the 3D of the region. Okay, and then you need to evaluate triple integral fxyz is equal to z and then dv. Okay, remember for type 1 region, you need to solve for dz first and then followed by dA. Okay, dA either you solve for dx dy or dy dx. It's up to you. So let's say I solve it using dy dx. And then substitute the limits for y and x first, the base first. This is our base. Okay, this is our base. So for dy dx, x is a fixed number. So x is from 0 to 1. And for y we have this. This is y equal to x, and then upper limit is equal to 1. So for y limit, we have x until 1. And then for z's limit, refer here, y and z plane. So this is z equal to square root 1 minus y square. And the limit, the region we consider is this one. Okay, so basically for z, we have z equal to 0 until this curve, this parabolic. So z from 0 to square root 1 minus y square. Okay, so in solving for triple integral for type 1 region, we have equal to 1/8. Moving to type 2 region, a solid region G that lies between the graph of two continuous functions, again of x and z, bounded left and right. Okay, and then this is the domain for the G, and then where R is the projection of G onto xz plane. So basically for type 2 region, the base is on xz plane. So the triple integral can be expressed as follows. Okay, we solve for dy first, as dy is the height of the solid, and then followed by dA. dA can be either dx, dz, or dz, dx. This is for type 2 region. An example for type 2 region. Okay, we try to find the volume of solid G bounded by z equal to 3x squared and z equal to 4 minus x squared, y equal to 0, and z plus y equal to 6. Okay, so first we have zx plane. Zx plane. Okay, and then z is equal to 3x squared. We have smiling face. Z equal to 3x squared. And then 4 minus x squared. 4 minus x squared, we have intercept at 4. Okay, so we have this region. So this is z equal to 4 minus x squared. This is our region. Okay, next we have zy plane. For zy plane, we have z plus y equal to 6. So when z equal to 0, y equal to 6. When y equal to 0, z equal to 6. And then this is the second region. So if we can view this in 3D, okay, z, y, and x. Okay, so we have here the base in z, this is z. Okay, this is the region. And then we have this one, y equal to z plus y equal to 6. So we have this. Okay. This 3D. It's not really good drawing, but I try at least. Okay. So for triple integral, the volume V. Volume means you have triple integral for solid G, and then we integrate 1 dV. Okay, so for this one, okay, so we have triple integral. Remember for type 2 region, the base is on xz. So we need to solve for dy first. We have 1 dy first, and then it's up to you to do dz over dx or dz. So I decide to do dz dx. Okay, so for dz dx, okay, refer to this sketching for z and x. X is fixed number, so you need to find what is this two value, the intersection. Okay, so this is -1 and this is 1. So limit for x is -1 to 1, and then limit for z is from 3x squared until this 4 minus x squared. So this is 3x squared, 4 minus x squared. Then for z's limit, the height is from this one. Z's limit is from 0 to this line. From 0 to this line. This line is z equal to 6 minus y. Y limit. Okay, we need to find y limit, dy. Okay, so for y limit, it is from 0 to this line where y equal to 6 minus z. Okay, so 0 to 6 minus z. And then, as usual, you need to solve for this triple integral. Okay, so as conclusion, to find the volume for this region, these solids, is equal to 304 over 15 when you solve this problem using type 2 region. Okay. The last type of region we have here is type 3 region, which is a solid G that lies between the graph of two continuous functions y and z, bounded back and front. Okay, that is given by this domain G, and then R is the base. Okay, projection of G onto YZ plane. So basically in type 3 region, the base is on YZ plane as shown in this figure. Okay, so the triple integral can be expressed as follows. Okay, so solve for dx first, integrate dx first, and then followed by dA. dA is either dy dz or dz dy. Type 3 region. Okay, we have few examples here. Okay, for the first example, find the volume of the solid in the first octane bounded by the planes y plus z equal to 4. So the first, we have z and y. Y plus z is equal to 4. We have this region. And y equal to x square. Y equal to x square. This is yx. XY plane and YZ plane. XY plane and YZ plane. Okay. So y plus z is equal to 4. 4, our intercept 4 is at y equal to 4 when z is equal to 0. So we have this y equal to 4 over here. So this is the region for XY plane. And if we combine this in 3D, z, y and x, z and y we have this one. And then for yx, we have this curve. This is 4. And then the base is on xy plane. So this is the solid. Okay. So the question asks you to find the volume again. So the volume you have triple integral. You need to solve for dx first. So dx first. And then followed by dy dz. Okay, dy dz. Okay, so limit for z. Limit for z is from 0 to 4, fixed number. The outermost integral is fixed number, and then followed by limit for y. Y is from 0 to this line. Y is from 0 to 4 minus z. 4 minus z. And last, limit for x. Limit for x, we see here, we start with x. The lower limit is x, and the upper limit is x equal to square root y. Okay, so x is 0, limit x is from 0 to square root y. So you know this is the volume for triple integral. And then you need to solve as usual, solve for this triple integral. So the volume for this solid is equal to 128 over 15. Okay, use the substitution over here to make your integration easier. Okay, use u equal to 4 minus z. Substitution u equal to 4 minus z. In second example, I will show you how to find the volume of a tetrahedron. Okay, when we have this plane 3x plus y plus 4z equal to 12 equal to x equal to 0, y equal to 0, and z equal to 0. Okay, how to sketch this region, this solid? Okay, so we have 3D, we have z, y, and x. Okay, refer to this plane 3x plus y plus 4z equal to 12. Okay, so to sketch for the first, we need to find the intercept of z, x, and y. So when y equal to 0 and z equal to 0, so x is equal to 12 divided by 3. So x is 4. And then for y, when x and z equal to 0, when x and y equal to 0, sorry, when x and z equal to 0, so y is equal to 12. So we have 12 over here. And last, for x and y equal to 0, our z is equal to 3. So this is your tetrahedron. Sorry, this. For this example, you can decide. They will not mention you need to solve either using type 1, type 2 or type 3 region. So you decide yourself either you want to do it using type 1, type 2 or type 3. For me, for this time, I will use type 1 region. Okay, type 1 region when my base is x and y. So this will become my base. Okay, next one, what you need to do is to determine these 3 line. What is the equation for this 3 line? Okay, so for yz plane, the line in yz plane is when x equal to 0. So this line is y plus 4z equal to 12. And this line representative of for x and y. So you have 3x plus y equal to 12. And for this line, since it is xz plane, so this is 3x plus 4z equal to 12. Okay, so this is the line, the equation for each line. Okay, so since I decide my base is xy plane, so my triple integral, okay, triple integral, this is the volume where I integrate 1. So I need to solve for z first. The height is our z. Okay, and then continue with dy dx for the first type. Okay, dy dx. So I need to know what is the limit for y and x. So the limit for x is obviously from 0 to 4. Okay, so 0 to 4. And then what is my limit for y? Okay, for y, you have here, y is from 0. Okay, it's come from here, y is from, sorry, it's come from here, y is from 0, and then it leave from this line. Okay, so this line, write your y in terms of x. So y is equal to 12 minus 3x. Okay, so my limit for y is 0 to 12 minus 3x. Okay, and for z's limit, you refer to this. Okay, so write z in terms of x and y. So z is equal to 12 minus 3x minus y divided by 4. So this is the upper limit for z. Because if you see from here, z is a plane. Limit z is a plane. Plane where z from 0 to this plane. Okay, x and y plane. So z's limit is from 12 to 3x minus y over 4. Okay, so solve for triple integral. Okay, right. After we solve for the triple integral, we get the volume is equal to 24 unit cube. Okay, so this is when I solve using type 1 region. Okay, remember type 1 region when the base is on xy plane. Okay, if you want to try for solving the volume using the type 2 region, okay, where the base is on xz plane. Okay, so you have volume equal to triple integral. You need to solve for dy first, and then followed by dz dx or dx dz. Okay, so for dy, write your y in terms of x and z. So y is equal to 12 minus 3x, 12 minus 3x minus 4z. And the lower limit is 0. This is 1. Okay, and then for dz dx, this is the base. Okay, for the base, x is from 0 to 4. 0 to 4, and for y, z's limit is from 0 to z equal to 12 minus 3x divided by 4. Okay, 12 minus 3x divided by 4. Okay, and then you should get this equal to 24 unit cube as well. Or if you want to solve this using type 3 region, okay, the base is on YZ plane. Okay, for YZ plane, you have the volume equal to triple integral. Then you need to solve for dx first, followed by y and z, or dx, dz, dy. Okay, anything. Okay, so for limit x from here, upper limit for x is from here. Okay, so you have 12 minus y minus 4z divided by 3. Okay, so 0, 12 minus y minus 4z divided by 3. And then for z's limit is from 0 to 3, obviously. So 0 to 3. And for y limit here, y limit is from 0 to this line. So y equal to 12 minus 4z. 12 minus 4z. For this one also, you need to get the last answer equal to 24 unit cube. Okay, so what I'm trying to say here is, if you want to solve for volume for the solid, 3D solid, you can use either, type 1, type 2 or type 3 region. Okay, you determine what is the base. Okay, and then solve the high first and then followed by the base. The z, for this one, z is the high. Okay, so dy dx or dx dy. We have another example here. To solve, okay, to use a triple integral to find the volume of the solid within the cylinder, x squared plus y squared equal to 9. So x squared plus y squared equal to 9. You have a circle with radius 3. Okay, and then the plane z equal to 1 and okay, z equal to 1 and x plus z equal to 5. So this is x, this is z. X plus z equal to 5 is over here. So 5, 5. Z equal to 1 is somewhere around here. So this is 1. So this is another region. Okay. So for this one, it just, okay, so this one, we have this. Okay, to solve for the triple integral, to find the volume. So V is equal to, let's say, we use type 1 region. Sorry, type 3 region, dx, dy. So we solve for dz first, followed by dx, dy. Okay, so dx, dy, we know for this, from here, we have y is from negative 3 to 3. This is negative 3 to 3. And z is, and x is equal to 9 minus y square. Square root of 9 minus y square. 0 to square root 9 minus y square. And then for z's limit, z is from 1 until this one. This line. So z here is equal to 5 minus x. 5 minus x. Okay, from here we have negative 3 to 3, 0 square root 9 minus y square. Sorry, this is the whole circle. So we have negative square root 9 minus y square. And then dz. So we have z 1 to 5 minus x. Dx, dy. Okay, so negative 3 to 3, negative square root 9 minus y square, square root 9 minus y square. So 5 minus x minus y, dx, dy. So we have to integrate respect to x next. So we have 4 here, so 4x minus half x square. Negative square root 9 minus y square, square root 9 minus y square dy. And when we do the substitution of y, we have 4 square root 9 minus y square minus half 9 minus y square plus 4 square root 9 minus y square plus half 9 minus y square dy. Okay, and then simplify this. You have negative 3238 square root 9 minus y square dy. And if you want to proceed with this integration, you will start here. Okay, you cannot move from here because you need to integrate square root 9 minus y square dy. If you have 8y here, 8y square root 9 minus y square, you can use the substitution. But if you have this kind of integration, it will be difficult for you to solve this. So this is an introduction to triple integral in cylindrical coordinates. We will try to solve this using cylindrical coordinates. 2.7 Triple integrals in cylindrical coordinates. Okay, rectangular coordinates in 3 dimensions with xy plane in polar coordinates. Remember, xy plane is polar coordinates. You have seen this before in polar form of double integration. And then for cylindrical coordinates, the type 1 is considered. Type 1, remember type 1 when our base is on xy plane. So basically this is the cylindrical coordinates. Okay, 3D in cylindrical coordinates. Definition 2.5. Cylindrical coordinates represent a point P in space by ordered triple r, theta and z, in which first r and theta are polar coordinates for the vertical projection of P on the xy plane. Okay, and then we have extra z. Z is the rectangular vertical coordinates. So basically z is our height, the height of the solid. Okay, xy is the base. Rectangular coordinates x, y, z are transformed into cylindrical coordinates such as, okay, you know this, x is equal to r cos theta, y is r equal to r sin theta, and z will remain as z. X square plus y square is equal to r square, you know this as well. And you need to know that tangent theta is equal to y over x. So you can find theta. What is theta? From inverse tangent y over x. Okay. One more thing you need to remember is dx dy dA. The dA is equal to r dr d theta. Okay. We have theorem 2.6 here. Suppose that fr theta z is continuous in region G and G is given by r theta and z. Okay, r theta real number. Okay, and z is written as k1 r theta and k2 r theta, where r is the projection of G onto r theta plane. Then we have this one. dz dA means dz, this is r dr d theta. You need to solve for z first and then followed by the polar. Okay, you know this. Okay, let's see the first example. Evaluate negative 2 to 2 limit for x, and then limit for y we have square root, negative square root, anti-square root, positive square root, and then z we have square root x square plus y square until 2. Okay, first thing first, always start with sketch the region. Okay, you know that dy dx is our base. Okay, so you need to sketch for yx plane. Okay, for yx plane, for y limit is from, you know this, y equal to square root 4 minus x square means you have x square plus y square, a circle with radius 2. Okay, so you know this. And then y limit cover the positive part and the negative part. So you have all this. And x is from negative 2 to 2. Okay, so you know the base. The base is a full circle. Okay, so convert this you have triple integral x squared plus y squared. You know the substitution for x squared plus y squared is r squared. So r squared, you have r squared, dz will be remain, dz, dy dx is equal to r, dr d theta. Then you have r, dr d theta. Okay. Okay, then find what is limit for r and theta. From here, r limit is from r limit is from 0 to 2. So 0 to 2. And theta limit, the full circle is from 0 to 2 pi. Okay, and z's limit, you have 2 for the upper limit. And for the lower limit, square root x squared plus y squared is equal to square root r squared. Square root r squared is equal to r. Okay, instead of you need to solve for this triple integral, you have all this square root. Okay, you can make it easier when you solve it in cylindrical coordinates. Okay, you can find this. This is equal to okay, you can continue from here. Okay, so you will have the last answer equal to 16 pi over 5. Now for the second example, use triple integral in cylindrical coordinates to find the volume of the solid bounded by x squared plus y squared equal to 9. X squared plus y squared equal to 9 means you have a circle with radius 3 on xy plane. Okay, this one. And then given z is equal to square root 25 minus x squared minus y squared, and z equal to 0. So basically this is the lower limit of z and upper limit of z. So you have triple integral. Okay, then you have dz r dr d theta. Okay, theta limit is from 0 to 2 pi. R limit is from 0 to 3. And for z limit, z is from 0 until square root 25 minus x squared minus y squared. So this is equal to 0 to 2 pi, 0 to 3. Okay, you can convert this x squared minus y squared. It becomes 25 minus r squared dz r dr d theta. Okay, solve for dz first, 0 to 3. Dz, z is 1. So you have z from 0 to square root 25 minus r squared. We have r dr d theta. Then 0, 2 pi, 0, 3. Okay, substitute the z. You have r square root 25 minus r squared dr d theta. Okay, you know this. When you find r multiplied by square root of 25 minus r squared, automatically remember that you need to use the substitution where u is equal to 25 minus r squared. So du is equal to minus 2r dr. And you can continue from here to get the last answer. Now you can compare your last answer with mine. The last answer I got here is 1 to 2 pi over 3. Okay? Okay, before I end this lecture video, okay, let's go back to our previous example, example 3 before this. Okay, so we can't do this using non-rectangular region, okay, using type 1 region. So what we can do here is to convert this or to solve this using cylindrical coordinates. Okay, using cylindrical coordinates, if we solve for this one, we know that our base, this will be our base. X and Y is our base. So for our base, V is equal to, okay, we have triple integral. Okay, in cylindrical coordinates, for volume, we integrate 1. Okay, dz r dr d theta. And for our base, we have a full circle, which is the theta limit is from 0 to 2 pi. And here our radius is 0 to 3. Okay. And our z limit is the same, 1 to 5 minus x. 1 to 5 minus x. Okay, now you can find what is the volume. Okay, so for this one, this is 0 to 2 pi, 0 to 3. Remember, in cylindrical as well as in polar coordinates, we don't have x and y. We need to substitute this x with r cos theta. 1 dz r dr d theta. Okay, for this one, we have 0 to 2 pi, 0 to 3. Integrate z respect to z. Integrate 1 respect to z is z. So we can substitute z. R cos theta minus 1. R dr d theta. This is our z. Equal to 0 to 2 pi, 0 to 3. 4. We have 4r minus r square cos theta dr d theta. And then integrate 4r. We have 4r square divided by 2 is 2r square minus 1 over 3r cubed cos theta. Limit for r is 0 to 3. So we have 0 to 2 pi. 3918 minus 2739 cos theta d theta. And last but not least, we have 18 theta minus 9 sin theta. 0 to 2 pi, and if we substitute 2 pi minus 9 sin 2 pi is equal to 0, minus 0 plus 9 sin 0 is equal to 0. So our last answer is 36 pi unit cube for volume. So the volume for this cylinder within the cylinder x square plus y square equal to 9, and between the planes z equal to 1 and x plus z equal to 5 is equal to 36 pi unit cube. And this can only be solved using cylindrical coordinates. Okay, so that's all for today's video. For the next video, we will end our chapter 2 with the last two subtopic, which are triple integral over spherical coordinates and the application of double integral and triple integral. We have moment, we have center of, we have mass, we have center of mass, we have inertia, centroid, and so on. Okay, that's it for today's video. Thank you.